Well, welcome to ISR Colloquium. This is the third in a series in this semester, and it's my pleasure to introduce our very good colleague, Ankur Srivastava. Just a brief background about Ankur. Ankur is an associate professor in the electrical and computer engineering department. He also has a joint appointment with the Institute for Systems Research. Ankur received his bachelor degree in electrical engineering from Indian Institute of Technology, known as IIT in Delhi in 1998. Master's in electrical engineering from Northwestern University in 2000, and PhD in computer science from UCLA in 2002. Ankur's primary research interest lies in the field of high performance, low power electronic systems, applications such as computer vision, data and storage centers, and sensor networks. He has published numerous papers. He has been actually part of a technical program committee of several major conferences in his field. And he is an associate editor of IEEE Transactions on VLSI and integration, known as VLSI Journal, very known journal in the field. He has received a number of prestigious awards, including Outstanding PhD Dissertation Award from Computer Science Department at UCLA, a number of Best Paper Awards, one of them at the ISPE 2007. He's the recipient of our prestigious George Corcoran Memorial Teaching Award in Electrical and Computer Engineering Department. And he's been featured in articles appearing in trade magazines such as EE Times. So many good things about Ankur, and he's really truly a person who collaborates with a number of our faculty in the Institute, and you'll see through some of his projects that he's going to talk about. So with no further ado.
Thank you. That introduction made me a little nervous, actually. But thank you for the introduction. And thank you for all for coming.
Oh, just wait. Thank you.
Thank you all for coming to this talk on energy and thermal optimizations in complex computer systems. So, a little briefly on the trends that we have witnessed so far. In the last few decades, the silicon industry has grown leaps and bounds. And mostly we have witnessed significant increase in integration densities, almost doubling every 18 months as predicted by Moore's law. And this increase in silicon densities is accompanied with a significant increase in energy and power that these systems take to operate. As shown in this curve over here, which probably is not very clear given the density of the slide. There are two components of chip power, leakage and dynamic, or static and dynamic. Dynamic power dissipation in large-scale digital systems is caused due to switching of transistors, and leakage power happens because you have a sneaky leakage current that you are always draining even when you're on, and even when you're not doing anything. Sorry. The component of so the total power has been increasing significantly over the last few technology generations, and the component of leakage has been growing at a much faster rate. So these are trends which are problematic for us because they lay a significant challenge in our continued development towards delivering better performance out of these systems. So higher energy is bad for us because it results in increase in system cost, weights and dimensions, smaller lifetime, and so on and so forth. In future, the energy problem and the power problem is going to become even more critical than what it is today, because the hope is that we continue to scale, we continue to fabricate silicon with increasing transistor densities. And not only that, we'll also use much more sophisticated integration technologies such as 3D ICs or stacked silicon, which will have an even higher energy and power footprint. Now, higher power dissipation results in higher temperature. And this is a plot, the thermal plot of a dual-core processor. This is the thermal plot of a single-core processor. And you can see that some of these areas can actually be quite hot, and they can heat up to beyond 100 degrees Celsius if not managed properly. Higher temperature is caused by high power density in localized areas, and high power densities of chip is not just high, it is also non-uniform. So there are significant, as you can see, spatial variation of power across the chip, and also the chip power shows significant variation in time as well, because as and when you schedule different applications, you do different jobs, you do multimedia versus internet browsing versus Microsoft Word, the total workload that these systems see varies in time, and therefore the power load that these chips have to support also varies in time. Higher temperature is bad for us.
Does the distribution of power change with time?
Yes, the distribution of power also changes in time. So not only the total power changes, but the way it is spread out across the chip is also variable. Higher temperatures are bad for us because it results in increase in device failures, reduction in lifetime, it causes erroneous behavior. And there is a very interesting phenomenon that leakage power exhibits. Leakage power is a very nonlinear function of temperature. So when temperature increases like this, then the leakage power increases rather exponentially, and that is bad for us. So higher temperature is caused by higher power, but it also causes even higher power dissipation. So there is some sort of a positive gain going on. So, and another interesting phenomenon is called as dark silicon, and there was a recent article in IEEE Spectrum on dark silicon which says that, which basically is the phenomenon where a certain percentage of transistors that is available to you, you cannot use, because you simply cannot support the power and the temperature overhead that 1 billion or 2 billion transistors pose to you. So about 20 to 25% of the transistors are actually unused. This is something that is seen in modern chips today. And this percentage of unusable silicon will increase in the years to come. So here you have a fabrication technology which is making a very large number of transistors available to you, but you cannot use it because you simply cannot allow all of them to dissipate power at the same time. And there's a nice article in IEEE Spectrum actually. Avi Cohen sent me that article. I didn't know about it. Anyway, so energy and temperature are actually, energy, power and temperature are actually different cost functions. They're not the same, but they are highly correlated. Energy is the total amount of power you use in a given time, right? Power is the rate of energy used, and temperature actually is a strong function of how power is spread out across the chip, both in space and in time. Okay, because the temperature at a given point is a function not just of the power being dissipated at that location, but also of the power in the entire environment. All right, so you can express these in nice mathematical equations. I mean, those I'm not going to go into the details of because they are rather well known. But they are indeed different cost functions, and they impact you differently. So CPU power, this is a very important aspect that we see in computer engineering. That the power that CPU dissipates exhibits significant temporal and spatial variations, and this is a challenge, but this is also an opportunity to us, as I'll discuss subsequently. There is a leakage thermal interdependence, as we mentioned. So higher power causes a higher temperature, and higher temperature causes higher leakage. So this is a problem for us. And another interesting perspective is that when you have higher chip temperatures, when you have higher temperatures that your computer systems exhibit, then you have to use some sophisticated cooling technology, for example, crank up the air conditioning. And so you have to use even more energy to cool the system down because you don't want to lose out on reliability. Okay? So these are ways in which higher temperatures increase the amount of energy you need to run correctly. So not only is higher temperatures caused by higher power, but higher temperatures also result in increase in power use and energy use. So how should we fix this problem? Well, I mean, a default approach could be to have better designs. Okay, you design a computer, you architect it in a certain way so that it dissipates less energy per operation, less power per operation, is more resilient to higher temperatures, and that would be one approach. But that is not what this talk is really about. Okay, this talk is about having this general notion of adaptability, which you see in real life all the time. We are all adaptable beings. Nature is adaptable, everything is adaptable. So how do you incorporate this notion of adaptability and exploit that for improving the level of energy use, the level of power use, resilience towards temperature. And how do you implement this general notion in computing? Okay, that's the focus of this talk. So, this is very true that modern multi-core CPUs have several control knobs, such as supply voltage, operating frequency of cores, task scheduling. So you have a bunch of tasks and you have 3 or 4 cores that can process those tasks. So which task should you schedule on which processor? Stuff like that. Issue with, if some of you do research in computer architecture, you know what that is. That allows you to trade off performance or power, energy, and temperature. So for example, if you increase the supply voltage, we all know that power increases, but speed increases too. Similarly, frequency. You increase the frequency, your speed increases, but your power increases, right? So the modern computer systems have these knobs that are available for us to manage, to control at runtime. Okay. But another factor is that the CPU power is a function not just of what these control knob values are, it is also a very strong function of what application you're running. Now, application workload that modern computer systems exhibit today fluctuates significantly. And this is data from Yahoo, and this is data from Oracle. And this is actually real data, by the way. Oracle found that their servers have such a workload pattern during different times of the day. So early morning, so this is rather obvious, right? And this is expected. No surprises there. So early in the morning, your workload increases significantly. Around lunchtime, it drops. And then it peaks again, and then it goes down significantly around evening time, right? And this is from Yahoo, where they were tracking how many videos people were requesting from the servers. But this relates to how much workload these computer systems have to handle. So at different times, different days of these months, the workload was rather bursty. It was unpredictable. It was not constant. It was not fixed. So application workload characteristics fluctuate from day to day and hour to hour, and that is something that these computer systems have to deal with. Even within an application, the program translates from one phase to the other. Okay, you fluctuate between a CPU-centric phase to a memory-centric phase. Okay, CPU-centric phase is the phase where most of the processing is happening at the CPU. Memory-centric phase is the phase where the CPU is waiting for data to come from memory. And for those of you who are not aware, memory is actually a very complex hierarchical system. You have cache memory, followed by main memory, followed by disk, and then you have flash. So there is a complete hierarchy. Okay, so and these programs fluctuate between these phases. So when you are in the memory phase, the CPU is not doing anything; it is just leaking out. That's it. And the actual workload is also data dependent, right? For example, if you have a for loop, the total number of times you take a loop is a function of the data that you are processing, right? So there is a lot of variability that applications impose. That the total workload that you want to process from a computer imposes, right? So the question is, can we exploit this variability for performing energy, power, and fuel optimization? And basically, is there a way to customize the behavior and the design of the computer system? And by computer system, I mean a very general term. I don't just mean central processing units that go inside computing devices such as laptops. I also mean data centers. I also mean distributed computing systems. I'm making a very general pitch here. Can we exploit this variability? For example, at times when you have less workload, you can change the design in such a way that you deliver only sufficient performance while minimizing energy, power, thermal overload, and so on and so forth, and doing the same when you have higher workload. So, how do you do this? That is what this talk about. So, conventionally, computer systems were viewed in a top-down fashion. You have all these applications, they are written in some language, C, Java, whatever, MATLAB, and then they are compiled, you get these instructions, the operating system schedules these instructions through some sort of hardware abstraction, and that's it, right? You go, you finish it, and then you are done. That's how these systems have been viewed conventionally. But this is what we are thinking. We are saying that maybe because there is significant variability across the applications, because the workload demands change across application to application, from one time of the day to the other, from one day of the week to the other. Maybe we can exploit this using this feedback system. Okay, let us suppose we have an infrastructure in place that allows us to collect information pertaining to the current state that the system is in, whatever that state means. It could be total energy use, it could be power, it could be temperature, it could be the level of workload demand, it could be cache miss rate, whatever, something, right? And then, based on this, and you sense it using some sort of a sensing mechanism. And then you create data, and from that data you get some knowledge out of what the state of the system is in. And then, using various control knobs, you generate a control policy that goes and manages the behavior of the system in real time. So that you deliver just the amount of performance that you need at minimum energy, minimum power, at the level of thermal load that you can handle, so on and so forth. Right? So that is the kind of system that we are anticipating, that we are hoping to build in the end. And in doing so, we will, in some sense, exploit knowledge that already exists in different other fields. For example, sensor networks or feedback control, and use some of that knowledge and some of that experience in building these systems, which allow this adaptability. Okay. So let's. So the salient features of such a system would be: you will need a system that allows you to sense. Okay, so you need some sort of sensors, whatever they are, and then you need a way of creating knowledge out of whatever data sensors give you. Now, sensors give you data that's noisy, that is not reliable. So you have to do some processing, some sort of signal processing. And then you have to do a synthesis of the control policy using that information. So all these three components have to be developed very judiciously while accounting for the trade-offs between various things. So let's first talk about the sensing aspect of things. And what I'll specifically talk about is sensing of temperature, okay? Because that is a very important problem today. So the problem of thermal sensing is that we are given a CPU or any VLSI system, and we'd like to, in real time, get information pertaining to the thermal state of the chip. What does that mean? It means this. It means that at each of these points, I'd like to know, this is a little cut by the way, I'd like to know what the temperature at each of these points is. Okay, that's my objective. How do I do that? Well, I have some sensors that we have present on chip, okay, and these sensors provide online data pertaining to the temperature at each of these points. Okay. And from that, I can try to, or I'd like to estimate the entire thermal profile of the chip. That's called the thermal profile estimation problem. In case you didn't know, thermal sensors are being allocated in increasing numbers in modern computer systems. For example, AMD Optron, which is a quad-core processor, has about 38 thermal sensors. i7 has more than 50, and the total number of sensors that future computer systems will have will be even more. Okay, so you need a nice, a well-defined methodology of allocating these sensors and reading from these sensors and generating the information that you need to generate. Yes?
So how much adds to the power consumption of the whole system as you add these thermal sensors?
Well, so, I mean, AMD quad-core has about 1 billion transistors, and 38 sensors is 7 inverters per sensor, so the total overhead is extremely low.
Low, yeah.
Right, so, yeah.
Well, nowadays, I mean, the designers will never let silicon real estate go to sensors. So how do you optimize what is the number of sensors that you need?
Yes, so we have done a little work, actually we wrote a paper last year, 2009, on how many sensors you need, how should you smartly, I'll talk about that. So yeah, you're right that if you go to Intel and you tell them, you know what, why don't you put one more sensor, they'll say get out of my office. That's their attitude. But if you see the trends, they are actually allocating sensors in increasing numbers. For example, IBM cell processor, which many of you are aware of, that goes in these gaming systems, has about 10 digital thermal sensors, whereas AMD quad-core has 38. So people are realizing that more and more sensors are needed. Okay, so thermal sensing is a challenging problem for various reasons. Firstly, sensors tend to be noisy. The sensor readings are a function not just of the temperature that they are facing at that point, but also a function of the design parameters, and also a function of the supply voltage, also a function of the ground. Now, VDD is not exact VDD, it's actually a fluctuating quantity on chip. ground is not pure zero, that is also fluctuating. And parameters of transistors that are used with these sensors are also random because your fabrication process is unpredictable. So thermal sensors are noisy, their behavior is unpredictable. And this sort of illustrates that. Sensors cannot be placed everywhere, as we mentioned. They can only be placed in areas where there is some white space available to locate thermal sensors. Generally, areas which have very high power density, you don't have enough space to fit a thermal sensor anywhere. So it is not like you're spreading sensors in the biosphere where you just go and spray sensors as if it's chloroform and sense everything. No, it is not that way. You cannot have too many sensors. On the top of that, temperature is a dynamic quantity. It is something that changes in space, as you can see, and it also changes in time. So we have to perform thermal estimation, or rather thermal tracking, in real time. And that is another challenge. So how do we solve this problem? Well, the basic problem is that sensors are noisy. Sensors cannot go into everywhere. So they provide limited information about the current state of the thermal state of the chip. And thirdly, we have to do dynamic estimation, right? So how do you solve this problem? Well, you solve this problem by using a statistical approach. Generally, it has been observed that the power dissipation at different points of the chip is correlated. It is random, but it is correlated. It is random because you don't know the actual characteristics of the application, the data is something that is unpredictable, all that stuff, right? But it is correlated, and because there is an underlying architecture that is doing that processing, and that architecture flows data in a certain fashion. For example, you always fetch an instruction, then you decode it, then you read the register files, or you do it simultaneously, then you go to the ALU, then you go to the memory, then you write back. So this is the pattern in which all instructions are processed, no matter what that instruction is. So there is correlation. And we found, for example, the ALU stage has, I'm sorry about the colors by the way, the ALU stage has a very high correlation with the power in the ALU state, ALU module has a very high correlation with the power dissipated in the instruction window. The power dissipated in the register union buffer has 0.61 bit. The power dissipated in the instruction window has about 0.91 correlation coefficient with the power in register union buffer. So there are correlations, right? So not only that, two modules which are placed closer to each other, even if their power dissipation is not correlated, purely because of physical closeness, their temperature is going to be correlated. So there are going to be correlations that exist between this temperature field at different points. Okay, so you can use these sensor observations to estimate the temperature, hopefully everywhere, right? That's the goal. So now we talk about the problem of using these thermal measurements in real time to perform thermal tracking, where thermal tracking is the problem of estimating this thermal field at all times. Okay, so your system is running, it is dissipating some power, you have a few sensors, and you are sampling those sensors at a certain rate. And these sensors are noisy, and these sensors are not everywhere, but we'd like to find at all times the value of this thermal field. Okay, so that's the thermal tracking problem. In order to model this as a tracking problem or as a state estimation problem, we have to describe the underlying physics that describes the dynamics of the state change. Okay, and that is not very tough actually. So if you have a chip. If you have a chip, then this chip, for all thermal reasons, could be represented as a distributed RC circuit. Distributed thermal RC circuit. So what you do is you take this chip, you divide this into grids, and each grid here is a node in this circuit. Okay, these resistances correspond to the thermal cross-coupling between adjacent grids, and these capacitances represent the heat storage capacity. Okay. And what I'm not showing here, but what does exist, is a current source at each of these nodes. Okay? And that current source represents the power that is being dissipated at this grid. Okay? And the voltage in this grid corresponds to the temperature, and the current corresponds to the power. So if you know the power dissipation profile, then you can write a very simple differential equation, first order differential equation, such as this, which describes the thermodynamics in the system. Okay, it's a very trivial thing. If you know this, then you know this, right? The problem is you don't know the power values at each of these points. If you knew, then you would be done. But you don't, because that value is strongly dependent on the application, strongly dependent on the data, so on and so forth, right? That is why you need sensing, that is why you need thermal sensing. So let us suppose you have sensors at a few of these locations which are being sampled at a certain rate, and you'd like to at all times find the value of the voltage or the value of the thermal profile of the chip. Okay. So this has been formulated in a standard conventional one-to-one estimation problem, right? So we simplify, because this is a continuous differential equation, we simplify this by linearizing it in time, or discretizing it in time, and we get this linear equation where Tn is the temperature vector of all nodes that represent the temperature at all nodes in this thermal circuit. N is the current time instance n, and it depends upon the temperature at the previous time instance n minus 1, using this linear matrix A, and P is the power dissipated at each of these points. This is generated by a simple discretization of this. Okay. So if you know P, if you know the power at each of these points, and if you know the temperature at each of these points, then you know Tn, right? Now the problem is that you might know what Tn minus 1 is, but you don't know what is Tn minus 1, because that's changing, right? So the next equation represents a sensor measurement. So Sm corresponds to the temperature at some of these locations, right? And Vn is the sensor noise. So this is a linear system. This is also a linear system. So the problem of estimating Tn from the sensor observations that we've had so far is a standard Kelvin filter formulation. There's nothing rocket science about it.
What is a good way of deciding the grid size?
Right. So usually what they do is the grid size is adaptive. So that's another huge research field, right? Like how do you generate this thermal RC circuit that represents
Accurate is a rule of thumb.
Well, I mean, you use rule of thumbs, for example, at places which have higher power density, you have more grids. At places which have lower power density, you have lesser grids. So, for example, the entire cache region might be 4 or 5 grids total, which is this big, and area, which is this small, might also be like 5 or 10 grids. So, you do it in such a way that each grid represents the same power. That's one rule of thumb. But there are inaccuracies in doing so, because then these resistances are not the same, right? So either you want a system where each of these resistances and capacitances are the same, or you want a system in which each of these power that is coming at these nodes is the same. So that's the trade-off.
So what you're saying is actually you don't need to have a uniform grid. You can have a grid.
You don't need to have a uniform grid, of course. Yeah. You don't need to. So the problem of estimating Tn using previous set of measurements is, yeah.
Ankur, we've had this discussion before. It's your assumption on P of n, the power, and you assume it to be Gaussian. And that's rather questionable, right? And the Gaussian assumption is important in getting the forms that you get subsequently. Is there any justification of the Gaussian assumption?
There isn't. So in reality, a mixture of Gaussian is a better model. That is what we found. That you have this set of applications, and each of these applications represent a certain typical power profile, and you can fluctuate around it in a Gaussian fashion. But if you change the application class, you have another, and you change with some probability. Then you have a different power profile, average power profile, right? And you can fluctuate around it in a Gaussian fashion too. But that the characteristics of that Gaussian changes from one application class to the other. And you can have any of these applications at any given time with some probability, right? So a mixture of Gaussian is a model. So I'll talk about that. So a pure Gaussian model is not valid. But it has been observed that you schedule an application and that application stays there, for example, 5 minutes or 10 minutes, right? In that duration, Gaussian is a reasonable approximation. Gaussian with known means and variances or fixed means and variances.
Now what I mean is that the bar is not negative, so the Gaussian assumption...
I see. Okay, yeah, of course. So this is certainly an approximation from that context. There are many approximations that are being done over here. Usually we are only interested in the expected value of the temperature. We are not interested in the worst case or the best case. So generally that negative samples don't really come into play because we are only interested in the expected value. But yeah, that is, as far as fundamental models are concerned, this model is invalid because power cannot be negative, temperature cannot be negative. If it is being modeled as an absolute temperature. So yes. We can also like model this in a different setting, right? I mean, you don't necessarily need to have a Gaussian assumption. You can use other estimation methods, particle filters, this and that, right? Which don't necessarily need things to be Gaussian. You can use real Markov models, right, with discrete probabilities. You can do all that. The thing is that if you have anything more complex than Calvin filters, you cannot do this in real time. So temperature on chip changes at the rate of a few hundred milliseconds. So imagine you have to sense the thermal sensors and then do all of this estimation in the order of a few milliseconds. So once again, it's a question of modeling accuracy versus runtime. So yeah, I mean, Gaussian is a approximation, and in a fundamental case, it is absolutely wrong. You cannot approximate this as Gaussian. Right? You can still use the formulas to estimate the expected value, and that is not so bad. Anyway, so you can set this up in a Kalman filtering perspective if you assume Kalman correctly, but still it's an approximation, that the power dissipation profile follows a Gaussian distribution or a jointly Gaussian distribution. Now that is not really true because different application classes, as I just mentioned, when you transition from one class of applications to another class, for example, when you go from multimedia to internet browser, or from Microsoft Word to checking email, whatever, right? You are going from one class to the other, and you do this as a user rather unpredictably. Especially in smartphones, this trend is even more predominant because the rate of behavior change is much higher in mobile devices than it is when you are sitting at a desktop. You know, people have done these user studies, people have done these characterizations, and it turns out that having mobility is bad for psychology because most of us are getting anxious because there's so much data that we have to do something all the time. But that's left for another time. So anyway, different application classes have different means and variances. So even if from that point of view our purely Gaussian assumption is wrong, because from one application class to the other you cannot assume that the means and variances of power is going to be the same. Actually, may change even if Gaussian is the right assumption to make. So you have to have a way in which your thermal tracker should be able to detect the fact that there has been a change of state and then recalibrate its Kalman filter so that it can continue to perform reasonably accurate estimates. So we developed such a system, and I don't want to go into the details of that because of that you can send it to you if you're interested. But these are the results that we got. This was the actual the blue curve is the actual temperature of a system. Okay, and these edges are these points of these non-differentiable points are places where there is a change of state. So the mean and variance of power here is different from the mean and variance of power here. Okay, and if you have a Kalman filter that doesn't change its parameters, doesn't recalibrate itself, then this is the qualitative tracking we got. And this is what our systems would get. Our systems which would recalibrate themselves at each of these points autonomously. It is not that you have somebody else telling the system that change your parameters. No, it detected change of state using various schemes that people had investigated and relearns the new parameters and restarts the estimation process. So quite accurate results compared to this. So there are several extensions that go on. There are several extensions that we have proposed in other subsequent papers, and one of them is accounting for leakage, temperature interdependency, and we've also investigated the problem of using this thermal data. So thermal data is pertaining to temperature at certain points on the chip, but the information that you can extract out of it is much more than just temperature. It has information pertaining to what kind of applications you are running, what kind of power dissipation levels you have, all that stuff, right? So we can not just track temperature, we can also track the power used, and this was a power tracker that whose various work talks about. So these are the kind of extensions that we proposed. Now fundamentally, the quality of sensing that you can get is determined by how well you design the sensing infrastructure. So where should the sensors go? What should the accuracy of each of these sensors be, how many bits they should be allocated, and how should you combine the readings together, how should you take the readings together, how should you fuse them and generate your estimates. So the talk up till now was more of the estimation problem, where you're given these sensor measurements, how do you put them together to make your estimates, right? But the question also is, where should these sensors go? Which parts of this grid should be sensed? How many bits of information should... So temperature here is a continuous value. You can represent it in 4 bits, you can represent that in 20 bits, right? So how many bits do we need here for a certain fidelity in estimate? Yeah.
Is it typical to have an analog to digital converter per sensor, or is it usually multiplexed to just one sensor?
There is a, so it's not an analog to digital converter. I mean, so one design is this oscillator-based design, but there could be others, and I think this is a better person to ask these questions. But you have these, for example, 7 inverters that are connected in this feedback fashion, and the frequency with which you oscillate 0, 1, 0, 1, 0, 1, that is a function of temperature, because that is a function of the delay of this. Okay? So all you got to do is, in a given constant time frame, how many oscillations that you have. So that's not a full-fledged A to D converter, really. That's just a counter. Okay, but yes, you have to have one per sensor. Generally, that's the infrastructure that people have investigated. You could try to reduce its overhead by having just one of this counter and multiplexing it, and then there's going to be some delay in sensing. You know, read one sensor, then the other, then the other, then the other, right?
Because I assume that delay is not all that essential, because you want to have one reading every few hundred milliseconds.
Well, that delay is not that essential, and that is one optimization one can do. But then again, the overheads here are so low. And as I said, that the 20% of the transistors you cannot use anyway, so that's nonsense. Okay. So why do it? Why have this? So you have to implement that multiplexing process in software or in hardware, and that itself has overhead. So, you know, generally most people don't bother, because you have enough transistors. You have enough transistors, trust me. The real challenge is how to use them and what to do with them, which is why people are doing research in multiple. That's just my view. Anyway, okay, so we came up with an algorithm that would, for a given power profile, for a given correlation and power profile, and so on and so forth, would allocate sensors, how many sensors where they should go, such decisions. I'll not go into the details of that algorithm, but this is the results that we got. This is the actual temperature in blue, and in green are the results from our network of sensors on chip. And this is from another competing work that somebody else had published earlier, which was not using correlation, which is using a different way of spreading sensors, which I will not go into the details of. The point is that this is an important problem, and there are important things you can do to do better estimation. Another interesting trend that we saw was that there is this fundamental question that folks in sensor network always ask, right? Should we have a lot of weak sensors, or should we have a few smart sensors? And certainly the trade-off lies somewhere in between. And we saw this trend here also. So we had this network of sensors, right? And where you were allocating 16 bits total to represent all the information that you want to store, right? So as you increase the number of sensors, the total number of bits per sensor is going down, right? So initially the RMS error in your estimation went down, and then after a certain point it began to increase because the total number of bits available per sensor was not that many. And you had sensors, you had too many sensors which were not very accurate, and that's bad. So there is a number. Anyway, time is sort of running short, so I'll try to rush through and talk about the basic top-level ideas that we are trying to pursue and not individual results. So the next question to ask is that we have all this estimation, sensing going on that can provide an online understanding of the current state of the chip, whether it's temperature, energy, power, state of virus attacks. You can estimate stuff like that, right? What do you do with it, right? From the context of temperature, you can make some decisions about changing various knobs of the CPU in such a way that you achieve better thermal management. Again, that problem is called as dynamic thermal management. So you have sensors which are providing this information, and now the problem is how do you do this part of the loop, right? So we implemented a very simple policy where what we were doing was that we would wait for the CPU to heat up, and we look at the sensor measurements, and as soon as the sensor measurements are very close to the maximum temperature, we shut it down. Shut the whole damn thing, okay, for a certain timeout policy. And then we turn it on again after that timeout, okay? So this was the performance of our approach compared to blindly trusting sensors. If you blindly trust sensors, the sensors are noisy, you're not doing any holistic estimation, you don't know what exactly is going on. So what is going on is that the green solid line represents the actual temperature, and the dots represent sensor measurements. Okay, so you are measuring sensors, and the temperature is increasing like this. And when you reach this point, the sensor, because it is an inaccurate version of the actual temperature, overpredicts. Okay, so it tells you that, you know what, I have reached my thermal constraint, you better shut down. Okay, but because that's an inaccurate decision, you end up shutting down too much, and that hurts performance. Okay, as compared to this case where we still have error, as you can see, right? But this error is not as high as the error here, so we are not shutting down as much. So decisions like these, and I'm not going into the details of all kinds of things that you can do. The kind of things you can do is quite large. You can, for example, control the VDD, scheduling of tasks, frequency, a combination of all that, driven by these sensors. And I'm not really going through all the kind of things that you can do, but this is a little example of what you can do and what you can achieve. So there were other pieces of work that we did where we questioned the need for having a maximum thermal constraint. Most thermal management schemes say that if you reach 8500 whatever degrees Celsius, then you should not let your temperature go beyond that. That's an absolute constraint. But it's not an absolute constraint. In reality, the impact of temperature on integrated systems is integrated. Okay, if you consistently run your system for a long time at high temperatures, then it impacts your lifetime, it impacts your reliability. Sporadic violations don't really hurt that much. Okay, and so sometimes if you have a task that has a very critical deadline, and this is especially true in electronics that manage your vitals in an ICU and stuff like that, then you don't want, then you want to deliver that deadline, even if that means violating the temperature constraint. So Diksha actually did a nice piece of work, and it has some nice results of optimality in rather realistic scenarios. And I can send you the paper if you're interested, where the question that we try to ask is that we are given this CPU, okay, which essentially is represented as a distributed RC circuit for thermal reasons. And we want to increase the power dissipation in it as much as possible, where we pay a penalty for every centigrade increase beyond the thermal constraint. Okay, so I'm giving a very top level view, which I know you know this is not exactly what we did, but that's the general formulation. So that's an interesting control theoretic problem too. And in that case, the optimal frequency policy actually looks something like this, and it does result in helping us deliver when you need to, even if that means you need to violate the temperature sometimes. Okay. So these are the kind of things that you can do as far as temperature management is concerned. And recently we started working with some folks in mechanical engineering. And Peggy is here, he's a research scientist in MEC with Avivar Cohen. He's doing a lot of work on chip cooling. And specifically, he's involved in developing devices such as thermoelectric coolers, which are based on the principle of Peltier and Seebeck effect. So that effect basically is that you're given a PN junction. If you provide current through this PN junction, then one side will become cooler and one side will become hotter. Okay, so it's like having a refrigerator in the microscope. You can place these very close to those thermal hotspots, right? And this current basically forces you to expend some energy for providing cooling. Okay, so that's another dimension of optimization that you can focus on. Another interesting device that these guys are focusing on is called these microchannels, where you fabricate these channels in high density at the back of the chip, and you can flow some chilled coolant through it. Okay, and as the coolant flows through these channels, it heats up and it takes the heat away, and a significant amount of cooling can be achieved, as much as 700 to 800 watts per centimeter square. So that's significant, right? It is much more than the power density that CPUs have today. Okay, CPUs, I think, in the worst case, have something like 200 to 300 watts per centimeter square in localized areas. And overall CPUs for the whole chip have like 100 watts, 150 watts in that range, power dissipation. So a lot of cooling can be provided, but these approaches firstly are invasive. Right? You have to change the design, you have to incorporate these cooling devices in new technologies, and on the top of that you can, for example, change the flow rate of fluid through these microchannels and get better cooling. So there's a trade-off between, should I expend more energy to cool, or should I expend less power and cool down because I will do less work? Right? So if I do less work, I'm going to hurt performance, but if I expend more energy here, I'll hurt energy for the same temperature limit. So those kind of trade-offs can also formulate in the dynamic thermal management problem. So finally, I'd like to take this discussion and do a little bit of generalization from here. The discussion so far was mostly on standalone computer systems. You have one chip, and you have energy and power and thermal issues, and how do you incorporate this notion of adaptability, right? Where adaptability can be incorporated by having some sort of sensing going on and some sort of sensing-driven control, right? And that general notion has been investigated in other avenues, in other fields, but it's rather new for computing. Okay, but we can. But the discussion so far has focused primarily on standalone systems, which are very complex and which are going to get even more complex in the years to come. But what we are going to do with these systems is going to be even more complex, right? So we take these standalone computer systems and we're going to build large-scale data centers out of it. We already are. Okay, what about this? Is also a computer system. Okay, I mean it is not one chip, but it is a computer system. It's a very large-scale computer system. And energy and temperature issues in data centers are becoming a pretty big deal. In 2006, EPA reported, and I'm sure a lot of you already know these statistics, about 1.5% of US electricity consumption going into data centers. And they predicted every 5 years it will double. Okay, so already we are close to 3 to 4% of US electricity consumption going in data centers. And the place where it actually goes is, it goes in running the servers, which is directly correlated with the workload. And it also goes in running the air conditioning system. So each of these buildings, they have a very inefficient sort of a centralized air conditioning system, right? That is driven by sensors, sensor measurements from the air that is surrounding in the data center. Okay, and then you crank up the air conditioning if you sense that your air temperature is beyond 35 degrees Celsius. That's usually the constraint for servers, for server rooms. And that's how you manage this, and this is inefficient, and this has a huge energy footprint, which will only increase in the years to come. Another example of complex computer systems, which we can have a discussion whether you would like to call it a computer system, are distributed networks, right? I mean, so is a cell phone network really a communication network, or should you consider this as a hybrid communication computing network? So far, most of the people have, even the field of sensor networking, it has mostly dealt with the networking aspect of things. Okay, mostly. Okay, they haven't really viewed that as a computing entity that is doing something. So, for example, if you have an encoder and you have a decoder, the conventional view is that it's only interested in communication. But it is doing that communication by doing some computation. So you also have to look at the computation aspect of this system and see where opportunity exists to do energy and thermal optimizations there. So we have Dominic here who's leading that direction of effort in my group. So I'll spend a few minutes on that. So let's first talk about data centers. Data centers are very complex systems. Okay, and they have been built by combining already complex computer systems, right? Now, energy and power and temperature are very interestingly interdependent in those, right? Now, the reason why you have to crank up the air conditioning is because you believe, or the folks who make servers believe, that if the air temperature of the server is above 40 degrees Celsius, then it is bad for the chips. That's fundamentally the reason, okay? Right? That is a very inaccurate predictor of exactly what's going on at scale. And we set up a simulation environment actually which we did that. And we found that just because your air temperature is around 30-35 degrees Celsius, that doesn't necessarily mean that temperature at silicon is within safe limits. For example, most of the, more than about half, in fact, just about half of the chips in about 100 servers, that's your simulation environment, violate your maximum temperature constraint, even though the air surrounding that server was within its manufacturer's specified constraint. So you can crank up your air conditioning, you can maintain the temperature to be 35, but still it doesn't do what you want it to do. So that is one problem. On the other hand, a significant number is significantly less than the maximum temperature constraint, and that is bad too, because that means you are spending all this energy to cool when you don't even need to. Okay? So there is a need to combine all this effort that different people are doing, including ourselves, who are looking at the problem of temperature and energy at silicon level, right, or at standalone computing level, and you have to combine it with these mega-scale, macro-scale models that try to control the environment of buildings, of data center, air temperature distribution, and so on and so forth. Because only after doing that can you exploit the opportunities that exist that allow you to run efficiently. So we came up with an interesting way of balancing workload across servers so that this doesn't happen. Okay, and we have written a paper, and then we can share the results with you. Where for the same level of performance, we could achieve significantly lower energy use in the air conditioning of such data center environments. So I'll skip the other slides, and I'd like to spend just a few minutes. And once again, Prakash and I have had a lot of discussions on this. So I'm expecting some questions from you. So let us suppose we have an encoder and a decoder, right? So this is an example of a communication system, right? And it is sending video frames. Let's focus on video because video is a lot of that, right? And there are two ways in which you can send this information. You can either use MPEG, and what MPEG does is that it exploits temporal correlation in video frames and it compresses data like that, right? And MPEG takes a lot of energy at the encoder, but little energy at the decoder. Very little, because the decoder workload is very, very low. You can do it in a different way, which basically takes inspiration from Weiner's. We've had discussions on Weiner's. She doesn't really believe that I know what Weiner's is, but that's another story. You can exploit Weiner's in this context too, right? Like you have some side information here. The encoder has already sent you all these frames. That is side information for you. Okay? So you take the side information and you predict what the next frame is going to be using some mechanism. And then the encoder doesn't really need to send you a lot of information. You already have enough, and you just send some correcting information from here to here. So you have the frame that you need to, and then you can move on to the next frame, right? Such a setup is decoder-centric. The decoder has to do more work, right? The decoder has to combine all the side information, make its prediction, collect data, little bit of data from the encoder, and then make its estimate. So we have these two extremities, right? On one side, we have the encoder doing all the work. On the other side, we have the decoder doing all the work. The question is, can you do something in between? Now, if you view this as a hybrid computer communication system, you will be able to exploit such opportunities, right? You can say, you know what, if the encoder energy is running low, let me just ship all the computation to the decoder, right? If the decoder energy is running low, let me bring all the computations back at the encoder. So let us suppose there's a controller that is running over here that is adaptively deciding. So once again, the notion of adaptivity comes in, right? That is adaptively deciding who does what and when. based on energy availability. Okay, and for example, if the encoder heats up, it says, you know what, I heat it up, let the decoder take care of most of the computation, and I'm just going to send a little bit of information. So this falls in a very nice framework, and I'm sorry for the resolution here, but these are the results that we got. Let's look at this benchmark. For PVC, which is predictive video coding, also known as MPEG, the maximum energy that maximum of the two, which is encoder or decoder, right? So here the encoder was using the maximum of two energies, about 134 units, and the maximum temperature of the encoder was 73 degrees Celsius. In distributed video coding, the decoder was doing most of the work. The energy was less, but still about 944, and the temperature here was 74.81 degrees Celsius. In our proposed adaptive scheme, which adaptively balances workload between encoder and decoder, the energy was rather similar to this guy, but if you look at the maximum temperature for both guys is much less than the maximum temperature for these guys. And this we could achieve, so let me read it out. This is 71.45, this is 74, and this is 73. So we could do that because we were adaptively balancing the workload based on who was in what state. The specific algorithms I'm not really going to talk about. We've also run out of time. But the key points are that there is significant opportunity for energy thermal management in complex computer systems. And by complex computer systems, I mean not just standalone computers or computer chips that you see. That also includes what you build with these large-scale data centers, networks of systems, network of smart cameras, smartphones, whatever. Okay? But the way you do that is you must exploit the interaction between different levels in the system, and you would have to sort of combine models from micro scale or nano scale all the way to the macro scale or system scale, and that is a big challenge. Autonomy and adaptability would have a key role to play. Okay, you have to be adaptable. You have to be able to change your behavior, change your organization, change your policies based on need. Okay, and you have to have an infrastructure in place, a sensing and control basically, a sensing-driven control basically that allows you to do that, and autonomously. And we have unique concepts of unique combination of concepts from different fields, so one has to be very cross-collaborative. I'd like to mention the fact that the underlying principles of distributed sensing, estimation, and control is not unique to computer systems. It has been investigated in different contexts, but it is very new for us in computer engineering. And the hope is that the notion of adaptability and the experience thus gained would hopefully help other fields as well. And one question that one can ask is, can we take inspiration from biology? Because biology is adaptable, it is evolvable, so can we take some inspiration from there? So would hopefully help other fields as well. And one question that one can ask is, can we take inspiration from biology? Because biology is adaptable, it is evolvable, so can we take some inspiration from there? So that brings us to the next talk.
Okay, we have time for a few questions. Thank you.
I have a question kind of following up on the last part of your discussion here with distributed computer systems versus more centralized computer systems. Could you then speculate on cloud computing types of architecture, which would seem to be far more focused at one location versus distributed, which are non-cloud computing, basically what we have now, as it relates to energy and thermal issues?
So, there are two things here. Firstly, how are you actually physically building this computing infrastructure? In a cloud setting or a data center setting, whatever, right? And the question is, the other aspect of this is, what do the end users get to see? Right? So there is an aspect of physical distribution and allocation and management, and then there is an aspect of virtualization, right? And there's a trade-off between the two. If you put everything together, The hope is you can do better management. Hope, right? But usually centralized everything is bad if it becomes too big. But as long as the size is not unwieldy, if you put everything together, then you need less virtualization, right? But if the size increases beyond a certain point, then you become extremely efficient, right? Which is why you have to divide it into smaller chunks and distribute it across, I don't know, different offices, different buildings, different states, different countries, and but then you need a layer of virtualization. That to the end user, it shouldn't seem where his or her request is being sourced from. Okay, and it is increasingly becoming clear that virtualization is a very, very big opportunity in cloud and in data centers too, but more so in cloud. Especially because cloud is cloud because it has a rather diffuse boundaries, right? That's what cloud means in reality also, right? So in cloud computing scenario also, it's not that you have an infrastructure that's fixed. You customize the availability of your hardware based on your demand patterns. So you have bought like 100,000 computers, but if you only need 20, you only turn on 20 in one part of your building. That's really how it is done, right? But to the end user, it should not they should not feel that this is what is going on. So virtualization actually has a huge, huge energy and thermal overhead, and it is unclear how to manage it. So I think there is going to be a trade-off. There's going to be a middle point which will be optimal, right? You have some amount of decentralization and some degree of centralization, and then you have a virtualization layer which combines everything together. And where that point is, we really don't know.
Most of what you've talked about has been to do with sensing things and then changing the operation on the fly of the system. Does any of it feed back into the design of the system? So, for example, maybe when you showed the mesh, the RC mesh of heat propagation through a chip, is that affected much by the design of the metal layers and things, and therefore you would maybe measure things and change the routing?
Yes, it is absolutely right. So far we have assumed that in our cabin filter setting, for example, the model doesn't change. The system model doesn't change. But it can. You can simplify it if your temperature readings are such that a simpler model can describe the behavior or any sensor readings as such. So you can do that, but that's not a design problem still, right? That's still a modeling problem. So you have something that has been designed, that has been fabricated, that is in use. The question is, how do you model it? You can model it with a very, coming to your question, you can model it with a very detailed model, which is very complex to analyze. Or you can use a simpler model. And then how do you switch between the two? Can you choose one model over the other? And that's something we haven't looked at, but definitely is on the list. Now, can this feed back and change the design itself? Well, now it depends upon what is designed. If I have an FPGA and I reconfigure it, am I changing the design really? I'm not changing the design fundamentally really, right? Because my FPGA is still my FPGA. But will it go back to Xilinx or go back to Intel or go back to IBM, all this data, and in the next generation, in the next design iteration, they will change the way they are going to do business? Certainly they can do that. As a principle, why not? Okay.
Here.
Yeah.
No cause.
Oh,
Let's say you have a system that you have many cores on a single die, or you have many computers in one data center, and you're trying to control the temperature. And it's given that you're not able to move jobs from one place to another. You need to keep them in place.
Okay.
And you're dealing with these temperature constraints, and different things might be happening in different places. Do you have any experience on how to control this kind of system? Is it better to do one central control or distribute the control to different components? Because the distributed control itself is a very complicated
Exactly.
thing to do.
So we tried to. So over the summers, we tried to look at this problem actually. We were trying to investigate. So we tried to investigate this problem. It's not exactly what we said, but it has the same feel. So we are given these 16-core processors, say, right? And each core has one sensor, and that's all it has. That's all the information that it has, right? It cannot read everybody else's sensor. If instead you had a system where you read everybody else's sensor, do this calculation filtering business, and then you do your control, the overheads may be too high for very fine-grained microprocessors such as Tyrera from MIT and others, right? Or maybe example, I don't know. So we try to investigate this framework where you don't need everybody else's temperature information. You are a core, you have access to your temperature information. Now what should be your policy? Okay, as soon as your temperature increases beyond a certain point, then you can use something to control your level of processing, your speed, or whatnot, right? But is that going to be optimal? Well, certainly it will not be as good as what the centralized guy can achieve, but it will be much simpler to implement. Right? So there is going to be this trade-off. In data centers, I'll tell you how they are interlinked, right? So communication between, and correct me if I'm wrong, communication between servers on the same rack is very high speed, but communication between two racks is not that great, but that doesn't matter whether you are in the neighborhood or whether you are like 100 meters apart. Okay, so it's all the same optical link, and then it takes the same amount of energy, delay, whatever, to talk to the server that is in the rack just next to you, or in the rack which is 20 racks down. So in that model, when you have that model, right, then you can assume that for a constant sampling cost, I can get anybody's information. Right? So that offers an interesting control theory problem. We couldn't really go very far with that. But yes, we have tried.
Okay, mine is very low level. You concentrate on the transistors, the leakage, and so forth, right? You ignore the wire part, and wires, like copper wires, also generate a lot of. Okay.
Actually, we don't ignore copper wires. I2 R loss can be very easily be modeled in the thermal RC circuit framework.
Oh, I see. Okay.
You can.
All right. Okay.
Because
Now,
what you have to do, the active layer has one node in the thermal RC circuit.
Yeah.
The wiring layer above has another node, and there is some I2R energy power coming in here, and some active power.
okay. Then how about using the carbon nanotube wires? Which the Intel is trying to do it in 10 years.
We have not pursued that really. Part of the reason is that I don't know even one company that is selling a computer that is made out of carbon nanotubes and carbon nanotubes. I did collaborate with Führer, and it was a very interesting collaboration. But part of the reason why I didn't go down that route was because manufacturability in nanotubes is so low that thinking of multi-core processors designed using nanotube technology, it's rather far-fetched. So why to work on a problem that is not real?
But carbon nanotube vias are real, actually.
So I don't know whether, I mean, in principle, if you can model carbon nanotube circuits in this distributed RC framework, then you can, this is a general framework, right? And you can use it in any context. So you can, then yes.
Okay. That would be the last question, Prakash.
He was
Sergio, go ahead. Last question.
Yeah, I have a couple of essential physics questions. First about efficiency. Why do you measure mostly the temperature of the processors or computers and not the power that goes into the processor? And secondly, why do you use temperature measurements? For example, in your example of the distributed and pegged encoding, decoding, and no power, which is...
Oh, we have done power too.
Oh, you had the power.
So we had power.
But I'm puzzled about efficiency.
So, let me tell you how sensing in CMOS technology is done. Once again, Pamela and our friend here, and there are probably bigger experts than I am. So you sense an electrical signal, whether it's current, whether it's voltage, something, right? And then that electrical signal has some correlation with the physical quantity that you're trying to estimate, right? In this case, what you're trying to sense is the frequency of the ring oscillator. That's the physical quantity that you're measuring, right? But what we believe it is heavily correlated with is the temperature, right? But the reason my sensor is noisy is because other parameters affect that reading as well. Okay, so we can use the same reading and deduce something else also, right? For example, if we know the temperature is not changing or temperature is given to you, right, and I'm getting different readings at different times from the sensor, then I can use that reading to estimate maybe the supply voltage fluctuations. Okay, so so what you make of those readings are different. It's like if you have a light sensor, I mean, is it really sensing light or is it not sensing heat? I mean, it can sense anything because at the end of the day, it is giving you a value which is a function of many parameters, right? So yeah, that's that.
Okay, let's thank our speaker, and Ankur is going to stick around so you can ask him more questions. Thank you so much.